Hello everyone, I'm Damien Alouges and I will present my poster about performance comparison between federated and centralized learning with a deep learning model on Hoechst images. So the abstract states that one of the main problems of working with medical data is data privacy because of the sensitiveness of the data. And one possibility to upgrade the data privacy when we work with medical data is to use federated learning. So here is a diagram of to present the federated learning. The idea to keep data privacy when we use federated learning is that there is no data sharing. Each source of data will keep their data for themselves, like clinics and hospitals. They all keep their database for them, and they do not share it. So every source we will call them clients. They will all them have a database and a model. Every model has the same architecture. So basically what we do is that we train each model on their local databases, and once they are trained, they will send their weight to a global server. The global server will aggregate the weights of all the models, and then it will send back the aggregated weights to the models, and then every model will be updated and train again, then send again the weights, etc. It's a loop. So everyone will do a train of every model, sending their weights to the global server. The server does the aggregation, send back the weights, etc. So here is in the experimental design part, we can see the difference in the algorithm approach between centralized and federated. The main difference is about the global database here. So in centralized, we put all the local database in one global database, and then we train the model on this global database. In federated, it's a bit different. So every database is separated, and so we create the model. We do not test it in the first round, but then after every round we will test it. We train every client. Then when each clients are trained, they send the parameters to the aggregation, the server to do the aggregation. Then the server sends back the global weights to the model, and we loop like that. As a material and method, we started from the Hoechst GAN. This GAN is a model developed by George Wolflin to create CD3 and CD8 images. So the idea is that the model take Hoechst stain image as an input and will create one CD3 stain and one CD8 stain image. The the idea is to make virtual staining images because the CD3 and CD8 stain are quite expensive and take a long time to make. So if we can create a CD3 and CD8 stain from the Hoechst images, it could be quite useful. To create a simulation of federation, what we do is we test two approaches. We will train a model on centralized, train a model on 4 clients, and train a model with 8 clients in federated. To do the aggregation of the weights, we'll use a simple average. We use a simple average because we will be in a cross-silo configuration. That means that there is not much clients and all clients can be trusted. And to evaluate the model, we use the MIR metric, the masked intensity ratio. It's a metric created by the creator of the model to evaluate it. So basically it's a signal to noise ratio between the fake staining and the real one. So we will compare the images of created by the model and the real one and look at the pixel intensity to see which image has less noise. So as I told before, we tested the model in centralized, in federated with 4 clients and in federated with 8 clients. Here in the table we can see the results of the MIR value of the 3 models. Basically what we can conclude is that Centralized model have better results than the federated ones, and that the federated with 4 clients and federated with 8 clients doesn't have much of a difference in terms of results. So to conclude, we conclude that the federated learning has quite an impact on the results of the model, and it takes a more longer time to train or more resources to train. So it has a big cost. So we have to conclude if it's worth the data privacy. To pursue our work on federated learning, we will do the same approach on another use case about transcriptomic data to predict the patient's response to anti-tumor treatments based on clinical and genetic information.